So in this video, we're going to graph tangent and cotangent. So to get started, again, I'm going to use a graphing calculator at gcalc. So you want to find it, it's gcalc.net. And the curve is y equals tan of x. So I'm just typing tan of x. And you notice this. I changed my window to be x min of negative 2 pi, x max of positive 2 pi, which is about 6.14. X scale is still 1.57, and the y min and y max be those numbers. So it looks really, really nice and neat because I can see exactly where my asymptotes occur at. If you notice, tan is this curve that the asymptotes on both ends here, and it's just a mirror image of that over and over and over again. It just constantly repeats itself over and over. So because of that, the tan has a shorter period than everything else. So if you think about this, this is pi over 2 on this side, or 1.57, and this is pi over 2 on this side, which is also 1.57. So if we think about that, if this is half a pi, and this is also half a pi, together, they give you a full pi. All right, so to actually find out why tan looks the way it does, which is all these little squiggly lines here, it might be best to start off by finding out the values of tangent and come up with a table of values. So it might be fastest to find out, well, tan is y over x, and on a unit circle, all these coordinates are good coordinates to start with. So if I find out tan of 0, it would be 0 over 1, which has an output of 0. Tan of pi over 2 would be 1 over 0, which is undefined. Tan of pi should be 0, tan of 3 pi over 2 is undefined, and tan of 2 pi should be 0. So if you think about that, I have a order pair 0, 0, and I have another order pair at pi 0, so this would be pi right in the middle of both of those. And then I have another order pair at 2 pi, so if I want to go over, I have a solution at 2 pi, and I have another point, and I'll typically have another curve that would look like this. So anyway, that's what it looked like. And to find out why the asymptote's there, it might be good to be able to cheat with a calculator. So if you want to find out numbers really, really close to, say, pi over 2, you can find the value of y equals to tan of, instead of saying pi over 2, let's think about degrees, because it's easier to think about that in degrees. So this was 90 degrees. Just to the left of 90 degrees would be 89.999. If you type in tan of 89.9999 degrees, what do you come up with? Well, the output should be 572,958, roughly. So when I get really, really close here, 89.99, I'm at 500,000. It's going up really, really high, really, really fast. You could have also tested it at negative 89.99. You've got the negative version of that, means you're going downward. So that clearly shows that as you approach, as x approaches, change the color, as x approaches pi over 2, in this case we approach pi over 2 from the left side, see what's happening there. So as x approaches pi over 2 from the left, f of x approach, if you notice, it went straight up, f of x approach infinity. That comes way back, a positive infinity. That comes way back from the first unit, just positive, not positive, negative. So that comes way back from the first unit. And if we look at as x approaches negative pi over 2 from the right, we'll see the f of x approach negative infinity. So that's how you graph the tan curve. Some important facts about tan and cotan is that the period is pi over b, and the amplitude, like secant and cosecant, does not exist. The horizontal shift is negative c over b. And we mentioned the word increments for a while, just so you know, you may hear the word critical points. So the critical points is going to be period divided by 2, and this is the same for both tan and cotangent. Some other important facts is the fact that tan of x plus pi, or tan of x subtract pi, actually gives the exact same function. So if I added pi to it, or subtracted pi from the angle, it gives you the exact same function. Mainly because it just changed your starting point. So instead of you starting here and having the curve look like this, because the curves constantly repeat, and have these asymptotes here. If you add pi to it, pi will be the middle point now, and it would just do the same thing. So if you actually graph them, you will not see a difference because they are the exact same function. So to add pi, subtract pi will be on this side, this will be a negative pi here, and then you get a function that looks like this, and an asymptote there. Clearly, because they have asymptotes, the domain of tangent is not all real numbers, it's all real numbers except those values that we have asymptotes up here, same thing with cotangent. And while we're at it, so that I don't forget to mention this, know this, cosine is an even function. Comes from unit 1. We talk about even and odd functions, and if you remember, even functions are symmetric about the y-axis. So symmetric about the y-axis. Next thing, sine is an odd function. So that means that it's symmetric about the line y equals x and the line y equals negative x. Simultaneously, not one or the other, but both at the exact same time. So those are like things that can come up within this unit, and next unit, and so forth. And I didn't want to go any further without actually mentioning those things. Cosine is even, sine is odd. That's just the truth. That's all I have. You can welcome to finish our work now.